guys, so today we are going to pick up where we left off yesterday in class. I just wanted to go over a couple things real quick. I know we were kind of in a hurry to get out of class when we were going over, or was it? Specific heat. Alright, so I just kind of wanted to review with you guys that specific heat is the amount of heat energy in BTUs transferred to achieve a 1 degree change of temperature for 1 pound of a given substance. Okay, so if you have 1 pound of iron, right? That's a poorly drawn iron ingot, okay? If you have 1 pound of iron and like 1 pound of insulation, okay? If you add a little bit of heat to this iron, say it's at 70 degrees, now it's going to go to 71 degrees, okay? But if you want to change this insulation from 70 to 71 degrees, you would have to add a lot more heat to it because it's an insulator, whereas the iron is a conductor. So the iron, because you only have to add a little bit of heat, would have a low specific heat capacity. Alright? Whereas the insulation, since you had to add a lot of heat, would have a high specific heat capacity. I have terrible handwriting. Please bear with me. That's why I type everything out. Alright? So, just know that. And then here, we have a little table, right, that you can kind of look over that shows the specific heat capacity of some different materials, right? So water has a specific heat capacity of 1. Real easy to remember. Water is a liquid, okay? But you also need to pay attention that water, when it's a vapor or an ice, or a vapor or a solid, actually has a specific heat capacity of 0.5, okay? Ammonia has a specific heat capacity of 1.12. Copper, right, really low, 0.09, whereas cardboard, yeah, actually, what's a good one? I don't really have one. Alright, but you get the idea, okay? Now, let's see. Alright, so we have pressure and temperature, right? We learned about pressure, okay? We learned that pressure is, force over area, so pressure equals force over area. We learned that there is air all around us exerting pressure, okay? And we learned about temperature, right? We learned that temperature is the measure of the intensity of heat. Okay? It's not the same thing as heat, but it's the intensity of that heat. So, real quick little fun fact, okay? Water is R718, all right? Meaning it's refrigerant 718. Ammonia, or NH3, is R717. That's just kind of a little fun fact for you. Okay? You also need to know that pressure and temperature go hand in hand. They're directly proportional, meaning that as the pressure increases, temperature increases. Think of it like this. If you have, if you have a ball of air, okay? And you squeeze it and you press it down, you compress it, right? What's going to happen? It's going to heat up because you're applying energy to it, okay? Thus, if we know the pressure that a refrigerant is evaporating at, we can determine its evaporating temperature and vice versa, okay? So the pressure of a refrigerant, directly affects the evaporating temperature. Okay? So, let me show you this video here real quick. You also need to know that phase changes are done at a constant pressure and temperature. Okay? Remember we discussed that if you have a pot of water, okay, and you are boiling it, right? It's going to reach 212 and it's going to stay at 212 even as you continue to add heat until it is completely evaporated. Okay, let's see real quick. Alright, here you go. I have a video for you guys. You can either pause this and play the video, or I'm just going to go ahead and play it for those of you who don't want to do that. The audio quality is probably a little better if you pause it, but either way, here we go. Oop. There we go. Alright, I'm going to play this video for you, and we'll talk about it after, okay? Alright, there we go. Let's see. I forgot that they don't actually talk in that video. Alright, so that's kind of what I do. That's kind of what I'm here for, is to talk about it. Alright, so. There we go. Alright, so. What was happening in that video? Alright, so you know how I told you guys that pressure and temperature go hand in hand, right? It's still on. We're still on this slide. It's still right there. What's happening is, I'll just go ahead and make another slide. That works. There we go. All right. So what's happening is this guy has a little flask. I cannot draw on this thing. Okay, he has this little flask, and what he does is he puts a stopper in it. Okay, and sticks a hose in that stopper, and this flask is filled with, partially with water. Alright? And what he does is he has this little hand crank, and what he's doing is that is a little pump, right? So he is drawing air out of this tube, and by drawing air, we agree that air exerts pressure. Oh, that's not broken. That air exerts pressure. Okay? So what he's doing is he is pulling the air out of there to lower the pressure. If you saw, there was a little gauge, okay, and it should have been going down, right? He's pulling pressure out of that container. So now, instead of this being at atmospheric, let's say 14.7 psi, right? He is lowering it down and putting it into a vacuum, okay? And by doing that, he is lowering the evaporating pressure, okay? Sorry, the evaporating temperature of that water. So instead of boiling at 212 degrees Fahrenheit, and there's a whole scientific explanation behind it for how the air is acting on the water molecules, and now it's giving them more space to kind of free up. But just know that he is reducing the pressure, and by reducing the pressure, he is reducing the evaporating temperature, right? So the temperature that water will boil. So now, instead of 212, that water is going to boil at room temperature, 70 degrees Fahrenheit. Because instead of being at 14.7 psi, it is at, I don't know what, I couldn't read the gauge. It was a real blurry video. But it is at a lower pressure. Okay? This is a really, really important concept, that pressure and saturation point, okay? Saturation point, boiling point, evaporating point, okay? All the same thing, okay? That they go hand in hand. And that by controlling the pressure of a liquid, you can control its boiling point. Okay? Here we have a little thing. Normally this would be animated, but it's not doing that right now. So here is what we call a vapor pressure curve. All right? So in this area we have a subcooled liquid, all right? And in this, we discussed that subcooled liquid was liquid that is below its saturation point. In this area over here, we have superheated gas, right? So gas that is superheated beyond its evaporating point or its saturation point. And then we have two pressure scales, one in PSIA, one in PSIG, right? So pressure on this scale, and then we have temperature on this axis. And then this line right here, is our saturation line, okay? And what this does is, this is where the liquid, in this case ammonia, because it's a vapor pressure curve for ammonia, the liquid will boil. So at this pressure and this temperature, okay? So let's answer some example questions with that. If a refrigerant is evaporating at 33.5 psig, so if ammonia is evaporating at 33.5 psig, what is the saturation temperature? Okay, so we know 33.5 psig. All right, let me erase all these doodles I made. Okay. Might be a little hard to see this. I have a GIF of it somewhere, right? But either way, 33.5, make sure we're on psig. Okay, follow this over. Alright, goes across this line until we hit our saturation point. That's when we know that we can move from either a liquid to a gas or a gas to a liquid. Okay? Now, all we have to do is go down and see that at 33.5 psig, if you have ammonia at 33.5 psig, right, it will change phase at 20 degrees. Okay? Now, another example question. If the refrigerant is evaporating at 70 degrees Fahrenheit, okay, what is the saturation pressure in psig? So the same thing, but opposite. All right? So if we have a refrigerant that is, in this case ammonia, evaporating at 70 degrees Fahrenheit, so let's go find 70, and follow it all the way up. Cannot draw a straight line on this thing until we hit our saturation curve, our saturation line. Okay, what is the saturation pressure in psig? Okay, follow it across. Now, you also have to notice that this is not necessarily to scale. Okay, because it's a curve. It's not this pressure scale is not necessarily to scale. I used to have a little thing here that would tell me that had it, but somewhere between 85 and 135.3. Okay. I believe I got this information from somewhere else, the 125.3, but we'll look at it later. Another example, okay, that's not listed on here, but it does kind of tell us, all right, is say that we are evaporating at no, this is the same example. Not a great example. All right. Either way, it would be somewhere between 85.3 and 135.3. A better vapor pressure curve would have more information. There's also tables that give us this whole information outlined, and we'll use those, okay? If you guys look at your saturation tables that I gave you at the beginning of this year, those will really help you, okay? And those will give you that information. But wait, we have to remember that this is only in regards to pure refrigerant, okay? The refrigerant may also have other gases air mixed in with it, which will skew these numbers and cause inefficiency in the system. These are called non-condensables and will be discussed later in the course. We're going to get to that. They mess with your system, but basically, if you have a line, okay, and it's supposed to be filled with 100% pure ammonia, okay, and you know that ammonia evaporates at these conditions, okay, that at 14.7 psi, it's going to evaporate at negative 28 degrees Fahrenheit, okay, but now you've got some air in here because someone didn't evacuate the line properly. You got some air in here all mixed in. Now this is not a pure refrigerant, and it's gonna have different characteristics. It's gonna skew these numbers, okay, just know that. Quick thing we're going to go over is properties of refrigerants. A good refrigerant will absorb as much heat energy as possible as quickly as possible, right? So it will have a low boiling point and a high latent heat of vaporization, okay? So like I said, ammonia is a good refrigerant. It has a low boiling point at negative 28 degrees Fahrenheit, okay? A good refrigerant is going to work like a heat sponge. All right. I had a little animation of a sponge in my other PowerPoint. I was kind of proud of it. Right. So here's a little sponge. Right. A good refrigerant is going to be like a heat sponge. Okay. It is going to absorb a lot of heat really quickly. Okay. And when it boils, when your refrigerant is boiling, it is going to absorb a lot of heat in the process of boiling, meaning it has a high latent heat of vaporization. All right. A secondary refrigerant, this is something that we use a lot. It's not going to be necessarily factored into your basic refrigeration system, but it is really good. A secondary refrigerant is normally a liquid chilled by the primary refrigerant, circulated through cooling units. See glycol. Oh, that's not the highlighter. It does not undergo a phase change. So like ammonia, like we've discussed before, is actually highly toxic, okay? So in areas where there's going to be a lot of people, what we'll do is we'll use ammonia as our primary refrigerant, since it has a really good cooling capacity. And then we will use that ammonia to cool down glycol, which is not going to boil, okay? It's going to stay as a liquid. But we're going to use that ammonia to cool down glycol, which will be sent to the heat exchangers and offices and stuff like that. We'll go over that at some point later in the course, but just know that's what a secondary refrigerant is. Some properties to know about refrigerants. I forget how long this chapter is. Okay, properties to know about refrigerants. You have saturated temperatures and pressures. All right, a refrigerant, you're going to need to know the boiling and condensing points at different pressures, right? And we don't know, you may have a great memory. I do not. Okay, so there are tables out there for this, right? It's good to know the boiling point at atmospheric pressure and stuff like that, but there are tables called saturation tables. Makes sense, right? That will tell you the saturation point of a refrigerant. You need to know the density and the density of liquid and gas at different temperatures and pressures in pounds per cubic feet. You need to know the heat content of liquid and gas at different temperatures and pressures in BTUs per pound. Okay, you need to know the specific volume of liquid and gas in cubic feet per pound, right? How much space does it take up per mass? Okay, so like air is going to have a higher specific volume. Oop. I don't know why I'm drawing this. Air is going to have a higher specific volume than, say, lead, right? Because it's going to take up because if you get a pound of lead and a pound of air, the air is going to take up a lot more space, a lot more volume, okay? And you also need to know safety things, and also things for just designing your system. Corrosive characteristics, toxicity, flammability and reactivity. Reactivity is one that's important, not only in from a safety concern if something happens and you get it on your skin or whatever, but also very important, like in the example that ammonia is highly reactive with copper. Okay? So you cannot, and it will corrode copper. That's also corrosive characteristics. It reacts with it and basically turns it into this like blue rust. Okay? It oxidizes. It kind of oxidizes it. Okay? So you can't use copper in an ammonia system. You also need to know the types of heat transfer: conduction, convection, radiation. I'm not going to go through all of these definitions. I know you guys can read, and I know you guys have been learning this forever. Conduction is if you touch something, right? If you see a pan sitting there and it's nice and hot, and you go and grab it, right? And it's a metal handle on it and it burns you. That heat transfer between the pan and your hand is conduction. It is two objects in physical contact with each other, right? Convection is the process of transferring heat by moving a fluid, okay? You also need to know that fluid does not equal liquid, okay? A fluid, scientific definitions here, all right, can either be a liquid or a vapor, and that's just because of the characteristics and how they interact. Okay, so if you have a fan, right? If you have a fan that is blowing air, hot air across you, that means that the heat is being transferred by the air. This is convection. Okay, natural convection uses the normally occurring currents in the fluid, right? So, like air circulating around a room naturally. Forced convection uses fans or pumps, like this example, to circulate the fluid. Remember that heat rises. So heat rising up to the top of a room is natural convection. And then also radiation. Radiation, a little more complicated, but basically you just need to know that radiation is the sun, okay? The projection of heat by the sun or by an open flame through waves, rays, or particles from one point to another without fluid or any other material for conduction, right? It's just rays in the molecules, okay? So the sun, that's a really crappy sun. It's kind of like a lion. There we go. Sun. So here's a little example of it, right? So conduction is the transfer of heat in that pan. Convection is the transfer of heat through this liquid right here. And then radiation is the transfer of heat by this fire. Conductors and insulators. If you know anything about electricity, exactly the same. Right? So conductors facilitate heat transfers. Conductors are going to be like your metals, okay? Things that transfer heat really fast. Okay, they transfer heat really well. These are going to be used for, you guessed it, heat exchangers. So heat exchangers in your system is going to be like your evaporators and your condensers. That's where you're going to want to use things like aluminum, copper, stainless steel, stuff like that. Insulators, when you don't want heat escaping or heat getting in, all right, they're going to be a barrier to the passage of heat. They can be made using cork, fiberglass, fibrous boards, foamed plastics, all that kind of stuff. They are used in walls, ceilings, and floors of cold rooms to insulate them, to slow down the inward flow of heat so that refrigeration can be used economically, right? You're not going to try and refrigerate, not the pen. You're not going to try and refrigerate a cardboard box. Okay? Why? Because all the air is just all the heat is just gonna flow in, right? You have a little refrigeration system trying to pump the heat out, get it out of there, and that cardboard is not a good insulator, right? He's just coming in. So what a lot of people will do, they have these things called my brain fart. Okay, but they have these panels where they'll have metal, like sheet metal, and they have insulation sandwiched in between it. Okay, like an ice cream sandwich. Okay, and that creates a wall, a wall of insulation, but it still has the rigidity of the metal. Just a little side note. They use it for like basically everything. Also, insulation is used as a pipe covering where temperature difference between where there's a temperature difference between the pipe and the ambient, right? So if you have a nice a pipe full of nice cold refrigerant flowing through a hot engine room, okay, you don't want that heat getting in. It's gonna jack up all your stuff, okay? You designed the system to where that refrigerant should be at exactly that temperature. You don't want that getting messed up, so you should insulate that pipe. Alright, so we learned about how heat flows. We learned about what helps heat to flow. Now we're going to learn about the rate of heat flow. So, ton of refrigeration. This is a definition you need to know. This is something you need to memorize. I would pick one of these. Honestly, I would pick 12,000 BTUs per hour, but that's just me. Ton of refrigeration is the heat energy applied to melt 1 ton or 2,000 pounds of ice at 32 degrees Fahrenheit in 24 hours. It is used to measure cooling capacity, right? So some guy a long time ago took 2,000 pounds, 1 ton of ice, okay, and was like, how long, in 24 hours, how much heat has to be applied to this to melt it completely. Now, completely. Right? So, ton of refrigeration doesn't sound like a rate. Rates are like GPM, gallons per minute, okay? MPH, miles per hour. Doesn't sound like it. It sounds like a weight, right? But it is a rate. Rate, not weight. Okay? And that's something that you're just going to have to remember. You're just going to have to get past. Okay? So, if it takes 144, remember we learned the latent heat of fusion of water, right? We learned that was 144 BTUs earlier. So if we have 144 BTUs per pound, okay, I'm just copying what's up here, and we are trying to melt 2,000 pounds, okay, 2,000 pounds of ice, then that's going to be 144 times 2,000. That's going to be 288,000 BTUs per, since 1 ton of refrigeration is defined as how much it takes in 24 hours, per 24 hours. Okay? Oh, sorry. I did that wrong. Yeah, I did that right. Okay. 288,000 BTUs per BTUs for 24 hours. Okay, pounds cancels out. You're left with BTUs per 24 hours. Okay. Now, we don't usually measure BTUs in days. Okay, 288,000. So that's why I said usually a lot of times we'll measure BTUs per hour or BTUs per minute. All I did to get this was 288,000 divided by 24. Okay, you get 12,000. 12,000 BTUs per hour. If you divide that by 60 minutes in an hour, you get 200 BTUs per minute. Easy peasy, lemon squeezy. Alright, so there are some other things that affect heat flow rate requirements. It's going to be the weight of the product, right? So how much your product weighs that you're trying to cool off, okay, is going to affect how much heat you're going to have to remove from it. The specific heat of your product, right? So you're going to have a different rate of heat flow depending on your specific heat. It's going to be easier to cool off iron than it is to cool off your insulation that we talked about. You also need the starting temperature of the product, right? So if you have steak coming in, I don't know how to draw steak. All right, you got chicken thigh coming in. Okay, fresh off the chicken, right? It's at 90 degrees Fahrenheit, and you're trying to freeze it. You're trying to freeze it to 20 degrees Fahrenheit. That's going to have a different heat flow rate requirement than if you've got ice cream coming in that's already cold. Okay, that's already cold at 30, I don't know what ice cream, 32 degrees Fahrenheit. Let's just throw a number out there, I don't remember. 32 degrees Fahrenheit, and you're just trying to keep it at 32 degrees Fahrenheit, that's a totally different ballgame, okay? Your starting temperature and your ending temperature are going to affect your heat flow requirements. Also, will there be a change of state involved in the process, right? So in this case, you're trying to get all the liquid in this chicken, and you're trying to freeze it. You're bringing it below 32, so that's going to be a different heat flow requirement. And the time required to reach each desired temperature, okay? If you're trying to freeze something, flash freeze it, different heat flow requirements than if you just sticking something in the freezer and waiting for it to freeze, like popsicles or something, right? Let's see where we're at.